There'll be a, I'll figure out later how to turn off the camera. I know there's a way to do it. I just don't want to do it right now while you're all watching me. So we are recording. So everything you say right now will be held forever in YouTube land. Okay, but my voice will carry more than yours because the microphone's right by the computer. All right, so we missed a day of class. I don't know, fortunate or unfortunate, depends on your viewpoint. So we are going to jump right into that. And I think a good way to start this class would be to define what chemistry is. So chemistry, definition of chemistry is the study of matter and its changes. So how matter changes, or also, in contrast, does not change. So sometimes we don't want things to change. Sometimes we do. So the properties of things being both reactive and unreactive are important. Things like plastics, for instance, do not react very well. And that's a good thing because we put our food in it. It can be a bad thing if it's trash and stays around forever. Well, not forever, but thousands of years. Before we get into that, let me tell you about a very dangerous chemical. A chemical called dihydrogen monoxide. Has anyone ever heard of it? A couple people, yeah. So let me tell you about dihydrogen monoxide. It is a greenhouse gas. It's a very powerful greenhouse gas, about 500 times as powerful than carbon dioxide. So it's a very, very powerful greenhouse gas. It was, they found it in Fukushima. It was used in the Fukushima nuclear plant before the explosion. Remember that happened a couple years ago. We find it in cancer cells, use it extensively in animal research, and the U.S. military has a huge investment in its use for warfare. So should we ban DHMO? A whole bunch of websites on this. So this is something we should go and ban. Ban dihydrogen monoxide. So if you, some people are smiling, if you're in the joke, dihydrogen monoxide is water, H2O. And it's just the whole idea. So a lot of people are afraid of the word chemical. So also another word that seems to be increasingly scary is solvent. So someone brought me a can of paint and it said it's solvent free. I'm like, well, not really. So solvent we'll talk about later. Solvent is just what things dissolve in, which is frequently water as well. So it probably means hydrocarbon free, at least hydrocarbon solvent free. Anyways, everything I said was true. Water is an extremely powerful greenhouse gas. It is the greenhouse gas for the Earth. So if you look at like Mars has about 20 times as much carbon dioxide than the Earth does. And it's very cold on Mars. There is a greenhouse effect on Mars, but carbon dioxide is not a very powerful greenhouse gas. Water and other polar molecules are very, very powerful greenhouse gases. So, if it wasn't for water on the Earth, it would be much, much colder here, even with lots of CO2. Used in Fukushima, nuclear power plants, most of them, at least electrical power generating ones, use water to transfer heat, and also, at least in the United States, and everywhere except for Canada, they use it as a moderator, slows down neutrons. So Canada, they use heavy water instead of light water. This is what's in here that I got from my faucet at home. It's light water. So heavy water is just deuterium. It's a proton and a neutron, and it's a proton. Found in cancer cells. Water's found in all cells, right? Animal research, you gotta give the bunny rabbits water to survive. Huge investment in warfare. Yeah, ever heard of the Navy? Right. So, like I said, everything I said is true, but people can take facts and twist them and make them sound bad. And this is one of my attempts. This is my attempt to try and hook you. So, oh, it's not full screen. So, this is one of my attempts to try and say, maybe we should study science. It's beneficial to study science. So, let's talk about science. Definition of science. So, maybe you hear someone say, oh, I have this down to a science. What do you mean when you say I've got this down to a science? Science means a systematic approach to solving problems. That's a system. The system is a science. And specifically, sciences use a scientific method. And let's talk a little bit about the different types of sciences. We have, these are kind of considered the main three. There are other sciences than this, but at least the ones that we have the most investment in, and also where we have the most people, biology, physics, and chemistry. So biology is the study of life. Physics is a study of forces and the, it's the physical world. Physics is the study of the physical world, but you have physics and physical world in the same definition, so I didn't like that one. To me, physics, in a way, is kind of how long is the vector and where it points. My gravity, my weight is at my center of gravity pointing straight down towards the center of the Earth. That's my weight, and then the force of the floor is pushing back up perpendicular to my weight, and the equal opposite forces cancel. So that's kind of like what you learn about in physics. Chemistry, we study matter. Okay, so matter is the central part of chemistry. And also, whenever you study matter, you're doing chemistry. So lots and lots of people do chemistry. They don't realize it. So if you go and work for Maui Brewing Company and you're doing stuff there, you're studying, you're doing chemistry. If you're looking to see what the specific gravity is of the beer, that's chemistry. So although I know there's also biology there, right, if you do the yeast and that kind of thing. And I mean, but chemistry is everywhere, at least as far as an economic point of view. Chemistry is also extremely political. So a lot of sciences are extremely political. So I guess 2 weeks ago, I think, like for instance, there was a 200 million plus lawsuit handed to, or someone sued Monsanto and got a $200+ million award. So lots of things you see in media, lots of things you see in courts. Of course, there's other types of sciences. There's geology, so study of the earth. If you oceanography, studies of the oceans. So, but I'm kind of trying to focus down on small things. In chemistry, we have 3 main branches. So synthetic and physical. If you remember in the intro, I talked a little bit. I'm a physical chemist. Since synthetic chemists, that's the people that actually make things. Most people are synthetic chemists. The majority of chemists are synthetic chemists. There are fewer physical. And this is an increasing branch, biological. So biological chemistry has been growing in its identity. Okay, so we talked about science and scientific method. Let's go back and talk about the scientific method. So here are the main steps, and typically start with observations. So observations can also be either quantitative or qualitative. So quantitative, quantity, number-based. Qualitative, idea-based. So I'm looking at the back of the classroom now, and there's this it's a bluish wall. We have a blue wall. Qualitative. Quantitative, the color of the wavelength coming from that blue photons from the wall is 550 nanometers. That's quantitative. When you slap a number onto something, it becomes quantitative. If it's an idea, qualitative. This is a small classroom. That's a qualitative argument. I have 20 registered students in this class. Quantitative, right? So put a number on something, it becomes quantitative. And let me jump just right to law. So a scientific law, and this, if you ever get confused by any symbol I use in class, I can use many different symbols. This is a math symbol. This is capital sigma. It means sum. So capital sigma means sum, and a scientific law is a summary of observations. So a simple scientific law is one called the law of gravity. What comes up must come down, right? So I could spend the whole semester verifying the law of gravity. That would be a very boring semester, right? So, can you break scientific laws? Yes. Right, the Voyager probes, they're leaving the solar system. They went up, they're not coming down. You can break scientific laws. Scientific laws are just a summary of observations. They're generally true. They're not always true. Okay, so let's talk about something else. What about another way? Sorry, I'm drinking water real fast. After lab, I ran and ate some food real fast so I could have more energy. So, starting with observations, one may form a hypothesis. A hypothesis is a guess based off, sometimes referred to as an educated guess. It's a guess based off of my observations. So, my car didn't start. That's an observation. I'm going to hypothesize that my battery is dead on my car. So now I can devise an experiment to test that. Like, well, if my battery's dead and I turn my lights won't work. So I turn the lights, oh, they work. The battery is not dead. Okay, so car still doesn't start though. Maybe I don't have any fuel. So what's my experiment? I'm gonna go and I'm going to add fuel to the car and see if it starts. I do, the car starts. Oh, I've just proven that my car didn't start from fuel. And then that confirmation is known as a theory. So confirming a hypothesis, then it becomes a theory. Of course, this is a very simplified, version of the scientific method. So there are much bigger theories, things like atomic theory, the idea that most matter, at least matter that we care about. Sorry for the particle physicists here, but or the ones listening online. That's probably. I gotta be careful where this camera's pointing. I'll get some interesting reports back to me. So things like atomic theory or germ theory. That was a big theory that illnesses are caused by pathogens. But even if you look at germ theory, that doesn't describe all illnesses. Some illnesses are not caused by pathogens. Cancer is not a pathogen, although some cancers may be caused by pathogens. There's radiation sickness. That's a disease. That's not caused by pathogens. And other things like dermatitis. So contact dermatitis can be caused by poison ivy. It can be caused by sticking your hands in bleach too long. So there's lots of diseases that are not necessarily covered by a single theory. So theories can be wrong as well. So, but theories don't necessarily describe everything. Like I just mentioned with diseases, you can't say pathogens cause all disease because they don't. There's diseases that are not covered. Pathogens. Other diseases that are not even like mental diseases or addictions like alcoholism. That's not either that's not caused by a pathogen. So, but the general idea is we have observations. We form a guess with the observations. We test that guess, and then we can prove, based off of experiments, that what we determined from the observations and guessing about what's going on. And things can be constantly revised too. So I don't know if we'll get to this class, probably not. We'll talk about atomic theory. And we started off atomic theory and thinking that atoms were like solid spheres, kind of like the pit. Like if you ever go to McDonald's, they have that ball pit. They thought that atoms were like that. They were like big solid spheres. And then we thought that atoms were kind of like blueberry muffins. So that's called the plum pudding model. We don't have plum pudding here in the United States. Well, maybe we do, but it's like a blueberry muffin where you have like a big muffin with little tiny blueberries in it. So instead you have a big ball of positive charge with electrons floating around in it. That's the plum pudding model. So we changed our idea. The atomic theory is correct, and now we have the quantum mechanical model. Can that be revised? Yet maybe string theory is going to come about, and then now we'll say quantum mechanics, that's crap. Where it's all about string theory now. And What's also scary is you can have a theory that predicts correctly but can be completely wrong. So for instance, let's go back to the old Greek idea of earth, wind, fire, water. Let's say that I go, all right, we have 4 elements, earth, wind, fire, water, and I can show you that there's fire and air. And let me do that by taking a candle and lighting it and putting a glass jar over it and then watching the candle extinguish. So the candle extinguished because there's no more of the fire in the air. And I can further prove that living creatures need fire to survive, because when I move around, I feel hot, I burn, so I'm on fire, I have fire in me. And then, so I'm hypothesizing that if I smother someone or another biological creature, then that creature will no longer exist. And I could prove that right. So, but I'm completely wrong, right? That's not what's going on. Of course, it's oxygen. Oxygen is what's happening. But that's what's scary. Theories can be wrong. And we also revise theories. Like I say, we learn more and more about things. Here are this. So hypothesis, it's a guess, theory proven fact. And theories can be and are often incorrect. We've got lots of theories floating around in this day and age, contemporary society, that we don't understand. Astronomy is full of them. So, chemistry is pretty well understood, at least at this level. Okay, there's a lot of chemistry study of matter. There's a lot we don't know about matter. I'm not saying like, oh, stupid to do chemistry research. No, we know there's still a lot that we don't know. But unlike astronomy, chemistry is extremely useful. So astronomy may be useful in the future, but I mean, unless you're like doing something like doing a Mars colony, I mean, a Mars colony would be a major economic drain. And so let's say I want to spend $1 billion studying cancer drugs. That's, why do you want $1 billion? Like, okay, well, that makes sense. I want to spend $1 billion on a rocket. Like, what are you going to do with the rocket? It's going to go to Mars. So what's that going to do to help me? What's that important? So that's, if you noticed, you don't see that much in the news or anything. There's no outreach for chemistry. Or there is some, but it's very little. It's mostly educational oriented. You don't see outreach for physics, biology, or chemistry, just because it's so useful. How often do you see outreach for like marine biology and oceanography? I mean, we've got a center here on island dedicated towards outreach for it, right? Occasionally you have those museums of science and industry kind of thing, or you have like the kind of exploratoriums kind of thing, but chemistry, we don't have to because we're so useful. So that's some of the reason why you're taking this class, is because chemistry is useful. So, but back to astronomy. If you look what's going on right now, if you follow, we have the Big Bang Theory, and so 13.8 billion years ago, the idea started a singularity, and then massive expansion event happened, and now the universe is like, okay, well, we're expanding. That's Hubble's law. You can see, okay, the galaxies are moving apart. That's Hubble's law. So then they found out, wait a second, we're not moving apart, we're going faster. We're accelerating as we're going out. And why is that? So they came up with this idea called dark energy. So what is dark energy? Like, it's a big we don't know. And then there's dark matter. Like if you look at the Milky Way galaxy and you sum up all the stars, and you look at gravity, you say, okay, well, the stars should orbit this way, but they don't. There needs to be more mass on the outside of the Milky Way galaxy. So how do we do that? Like, well, it's dark matter. What's it in? I don't know. And so they even come up, we have terms like WIMP and MACHO. So WIMP is weakly interactive massive particle, and I forget what MACHO stands for. So they're trying to say, okay, but we don't know what we never touched dark matter, we haven't synthesized it. So that's one of those things saying we have no idea. So, and so theories can be and are often wrong. I mean, dark matter, at least our understanding of it is going to be proved incorrect, I'm sure. Right? We're going to find, or maybe we'll just learn more about what these weakly massive interactive particles are. So, and laws can be broken. The other thing is science is tentative. So here in contemporary, what's the Age of Enlightenment, I think we're referred to as, after about 1850-ish, we are in the Age of Enlightenment where our knowledge is experimentally based. We care about what we can prove experimentally. So if you take us back to ancient Greece, if you look at things like the philosophers like Plato, he, the ancient, and well, even a lot before 1850, knowledge was theoretically based. So if you ever heard of Platonic love before, so the word Platonic, so Plato actually believed that there was a form, and he's in heaven. There was a heaven behind, he thought the sky was like a veil that had holes poked into it, and the stars were just glimpses of heaven. And there was this perfect something in the heavens. And then you would compare what's here on earth to what's up in the heavens. And his own Platonic love, he thought that Platonic love means different in contemporary society in ancient Greece. Platonic love was only between two men. So men could only feel true love, and it was completely detached. So it's a very, so what's it called? This, so I can't think of the word, but it's the whole detachment idea. It's I want to say, it doesn't matter. The whole detached. It's kind of it's not this. It's similar to the Buddhist belief, but that's the whole idea that we can have these beautiful ideas that are not experimentally based. And back before, like in ancient Greece, that was fine. That was totally cool. Now, need experiments. So things like string theory. I've said string theory before. String theory, it's a theory. It's proven mathematically. So string theory scientifically is not considered valid because it hasn't predicted anything that we can detect. That's one of the things that we're trying to do. We are trying to validate string theory through some experiments. We have not yet. The other problem with string theory is there's many different types. So string theory, it's that everything is down. They have these tiny strings, and depending on how they vibrate or move, they determine certain properties. And then different strings together do different things, and they can form things like a proton. Okay, and what's nice about string theory is that it's a form of physics that is close to tying everything together. Right now, we don't have everything tied together, meaning I can't start out with protons, neutrons, and electrons and come up with a tensile strength of steel. Or I can't come up with quantum mechanics and then general relativity, like the orbit of Mercury. I can't do that with quantum mechanics. String theory suggests that they may be able to do that. So that's exciting about string theory. But it's right now, as I speak on YouTube, it's not considered valid because we haven't experimentally determined it. So, and another common thing is correlation does not mean causality. So correlation and causality are not, one does not prove the other. And one of the more famous examples of that, and you see this everywhere. So one of the more famous examples in the past was polio and ice cream sales. They correlated that children would contract polio when there were high ice cream sales. And the reason is because of the summertime. This is Hawaii, we always have nice weather. But somewhere like in Wisconsin, you're not going to buy ice cream in December or February because it's cold and you just want to stay inside. And it's hard to go anywhere because the roads are full of snow. Summertime comes along, June, July, you're out in the pool, it's hot, you want to buy ice cream. And then they notice, oh, in the summer months, and when there's ice cream, maybe ice cream sales are causing polio. And they say, parents, do not buy your kids ice cream. It causes polio. And what's actually causing polio is a pathogen, and the reason why it was more in the summertime because people mix more in the summer. Okay, so people mix more, it's a pathogen, so then therefore it was traveled that more quickly. That's another example that things might have a common third factor. So, but that still doesn't necessarily mean causality. So ice cream sales and polio outbreaks are related, but not by causing one or the other. You can get ridiculous things that correlate. There's a whole website of that. It's like movies with Nicolas Cage in it and suicides by hanging. They're like, they correlate these things. It's like things, just ridiculous. Like, it correlates perfectly. So, what if I, did a survey, I'm like, how many peanut butter sandwiches did you eat in the last year, and how many flat tires did you have in your car? So, could we correlate that? Yes. Would they have any interaction? Well, that maybe. Maybe you could say the people that are more likely to get flat tires also eat more peanut butter sandwiches because they could drive to the store. It's hard to carry that on a bike. I don't know. I mean, so that's they're not related. And the other thing is, science is powerful. So science, we can send people to jail using science, right? It's enough. It's usable in our court system. And bad science, we can severely injure people. And here's a science, and we still use some of these terms. I even hate calling it a science. We use these colloquially, right? Eugenics. Eugenics was a science back in basically after the whole idea of genetics came out. Then eugenics came out, and it's the belief that we have different races of humans. So even today, you ask, like, what race are you? And the proper answer is human, right? Although according to 23andMe, apparently I've got a bit of Neanderthal DNA in myself too. So I guess I'm a mix. So, but the idea, eugenics is the belief that there's different races of humans, and that if interbreeding of humans is allowed, this will cause the extinction of the human race due to inferior genes. Okay, and so if you ever heard of anyone ever heard of the Loving versus Virginia court case in the Supreme Court? So you have, yeah. 1967, there was a series of laws called the miscongenation laws. So the miscongenation, like the classifications of biology, the genus. So the idea was these are actually different races of people. And it was actually a very white-centered law. The idea is that basically anyone who wasn't white could marry whomever they wanted. But a white person could not marry someone who was considered not white. And you can go to jail for that. And that happened. So the Loving couple, white male married a black female in Washington, D.C. Then they moved, it was legal to marry not whites there, whites and non-whites. Then they moved to Virginia, where they got arrested for being married. And there's a whole movie on that too. The movie is actually kind of boring. I read the court case, so I watched the movie, and I was like, Anyways, it went to the Supreme Court, and it was shot down. So all miscongenation laws. So now there is no conflict legally over who you want to marry. But it was based off of the idea of eugenics. I mean, that was the whole idea based off this law, was that bad science. And the U.S. government, not only that, we've sterilized about 300,000 women, mostly Puerto Rican. So there was mass sterilizations in effect in the United States. So I'm not going to mention other countries. I'm sure you probably see where I go with that, but I don't want to mention that. So what is bad science? And this is me. This is not Tro. Bad science uses correlation, relies on models instead of experimental data, and the other thing, consensus. There's no such thing as consensus. The whole idea of a discovery, discoveries break the consensus. So if there was if consensus was important, there would never be any discoveries. So, okay, let's jump back into chemistry then. Oh man, I'm flying through this. Okay, how are we doing? Some more questions? All right, so let's talk about chemistry. And in the beginning, here in the beginning, we are going to jump topics quite a bit. Okay, so there's going to be a lot of jumping topics. First one is states of matter, a solid. My cell phone is a solid. It has a defined shape, definite shape, defined shape, and a definite volume. So my shape here is kind of a rectangular prism, and it has a volume of about 50 milliliters. Okay. Liquids have an undefined shape, or undefinite shape, whatever one you want to use, but it has a set volume. So there is, well, 40 ounces of water in here. I drank a little bit. So what if I had a beaker? Now it's kind of a shape that you can't see through, but the shape of a cylinder. What's going to happen if I pour it into a beaker? It's going to have the shape of that beaker. And what if I pour it on the desktop? It'll have the shape of a pancake. But the idea is that if I have a half a liter of water in here, there's going to be a half a liter of water in the beaker, half a liter of water on the desktop. And if I was very careful, I could scoop it all up, and then I mean, of course, I wouldn't do it perfectly, but hypothetically, if I could, I would have the same volume, right? The volume of liquids does not change. And they're incompressible, more or less. Gases, on the other hand, gases have neither a set shape or a set volume. So if I grabbed the tire off my car and said, okay, there's air in this tire, what's the shape, what's the volume? Well, shape of the tire, volume of the tire. If I punctured it and all the air flew out, what's the shape? What's the volume? Well, shape of the room, volume of the room. So gases are the least defined. They fill whatever space they're in. And they're also compressible. So if you've ever gotten air in your brake line, you know that the way your brakes in your car work. So when you push down, your brakes work whether your car's off or on. It's a hydraulic line. You push your foot on the brake pedal, and that pushes on a line that has brake fluid, has a liquid in it, and it goes to your tires. Your tires have a clamp. So your tires are on a rotor. You have an axle coming there, and you have a rotor. And along them, there's these two clamps, and they clamp onto the rotor. And then the rubbing of metal on metal is what breaks your car. Well, it's not metal. It's the ceramic. It's the ceramic brake pads on the metal rotor. If it's metal on metal, then it screeches. So that's how your cars break. It breaks then by friction. So if you've ever had air in your brake lines, you push on the brakes, and then nothing happens. And it's also really easy to push on your brakes when you have air in the brake line. Because all you're doing, you're taking gas and compresses. Whereas if you have a liquid, you put the force so that it carries the force through the hydraulic line to your brake caliper. So, okay, and let's talk about solids. Solids can be two different types. You have crystalline and amorphous. So most everything is amorphous, meaning irregular pattern. Crystalline, so if you, can you see that on this one? This one's a little bit, my laptop here, it is coated in anodized aluminum. I can't see the pattern. Yes, I guess I can a little bit. So the surface of aluminum here on Earth has aluminum oxide on it, also known as sapphire. So sapphire is aluminum oxide. This is completely coated in sapphire, okay? And then you can go to a jewelry store and you can buy a sapphire there. So what's the difference between the sapphire in the jewelry store and the sapphire on this laptop? And the answer, number one, is the crystalline, right? Do you have a question?
Oh, no. The same.
So sapphire aluminum oxide, pure aluminum oxide is clear. It looks like glass. So the sapphires, the stones, the ones especially the blue ones, have impurities of iron and titanium in them. So it gives it the blue color. And there's another kind of sapphire that's red that has chromium impurities, and it's also known as a ruby. Rubies are actually sapphires. What we consider it's just because we define sapphire as aluminum oxide. So if we define aluminum oxide as ruby, then it would be sapphires are actually rubies. But either way, they're made of the same stuff. It's the impurities that gives them the color. And it's a crystal, right? So I mean, if you ever look at aluminum foil, you can see kind of these white kind of horizontal lines on them. That's the grain pattern, and we're looking at specifically is sapphire. So the white stuff, if you ever look at white stuff on aluminum, you're looking at sapphire. But it's amorphous. It's not a set pattern. Crystalline things have a regular pattern, and they're more rare, much more rare. So if you look at iron, for instance, 90% of iron is what's known as called the 110 surface. That's a very low surface tension energy surface, but there's other surfaces. The atoms are arranged randomly, but they tend to organize themselves in a lower energy fashion. Although, even though 90% of the surface of iron has a specific sort of pattern, it's still considered amorphous. So, because it's still not set. And so you might say, oh, well, there's a regular pattern here. Yeah, things tend to go to the lowest energy, like the surface of metals, but still, if it's not really perfectly arranged in space, then it's not considered crystalline. Okay. Now, again, we're jumping topics yet again. All right, so let me start by something least specific. So matter, least organized matter are mixtures. And there's, I guess it's hard to see here. So matter, so what we find all around us, so matter. So mixtures are things, okay, well, I'll get to that. So mixtures are either heterogeneous or homogeneous, sometimes called homogeneous. Okay, so have you ever seen milk from a cow before? Anyone ever seen milk from a cow? I have. What happens when you get milk from a cow? It separates. Yeah, it separates. So milk is a mixture, and fresh milk is heterogeneous. It's not uniform. Cream on top, milk on the bottom. When you buy milk in the grocery store, what does it say? It says pasteurized and homogenized. So that means that it's uniform throughout. The milk on the top is the same as the milk on the bottom. Whereas fresh milk from a cow, it's a mixture. It's an inseparable mixture. So you can take things like milk from a cow and you can break it into mixtures that are uniform. So cream and milk. And then you can take those mixtures, the homogeneous mixtures, and you can break them into pure substances, which are either elements or compounds. So milk is full of things. It's got water in it. It has calcium phosphate, so there's calcium in milk. There's fat, depending on, well, unless you have skim milk. So a little bit of fat. There's emulsifiers too in milk. Then let's see what else. Yeah, there's proteins, right? There's whey, there's casein, that kind of thing. So you can take milk and you break up into those. Those are actually all compounds. So compounds, and you have elements. So compounds are a combination of elements. And so elements are the least specific. And compounds then are still pure substances. So like water, H2O. I mean, it's nice having this class because most everyone probably knows that water is 2 hydrogens and 1 oxygen. So, but water is 2 parts elements, hydrogen to 1 part element, oxygen. And that's a compound. It's a combination of elements. And the compound is nothing like its original stuff. Water is nothing like hydrogen or oxygen, right? They're both gases at this temperature. It's very reactive. Hydrogen is very reactive, so oxygen is even more reactive, right? So oxygen will do all sorts of, like oxygen by itself will burn steel. Water won't, unless you heat it up super high and turn it back into oxygen. So also different combinations of elements mean different things. So we have water, H2O. There's also hydrogen peroxide, H2O2. And if you drink water, that'll quench your thirst. What happens if you drink hydrogen peroxide? You'll burn your throat and maybe die, right? So just adding another oxygen completely changes the compound. Okay, so now let me talk a little bit more elements. Whole idea. So let's say I have a long carbon rod, and I break the carbon rod in half, and then I take that carbon rod, I break it in half, break that in half. I get to a point where if I break it in half, it no longer becomes carbon. So I said this stuff is carbon, and I keep on chopping it in half, chopping it in half. And I get to this point like, well, I break this part anymore, it will no longer become that element that I describe it as, and that point is an atom. So uh, if we can break atoms apart. You can rip carbon apart into three heliums, for instance. That's how they make it in stars. Stars take three heliums and turn into a carbon, right? So, or we could, so whatever three, we turn into two lithiums. So uh, we can break atoms apart, but lithium and helium are much different than carbon. And okay, so let's go backwards then. We have elements. So we can take elements and we can use them to form compounds. And then those combination of elements and or compounds, we can then make mixtures. So we can make mixtures that are uniform. So we can take elements and we can make uniform mixtures that are uniform. Things like 14 karat gold. So it's about half gold and about, I don't know, it's copper, silver, gold is what 14 karat gold is. It's an alloy. It's a unified mixture. It has only 3 elements in it. Okay, so you can take elements and you can form a homogeneous mixture. Okay, and you can also take compounds and make a homogeneous mixture. Right, I can take the compound NaCl, sodium chloride, and mix that with water, and I can make salt water. Right, so and I can take elements and I can form heterogeneous mixtures as well, even just 2. I have a ring. I usually don't wear rings, but I have a meteorite ring. It's a nickel iron ring, and nickel and iron only exist in certain phases, meaning you have mostly nickel and a little bit of iron, and the other one you have mostly iron and a little bit of nickel. There's little stripy patterns in it. It's really pretty, and you can so with just 2 elements, it's not uniform. You can make a heterogeneous mixture. Of course, I've already mentioned things that are mixtures, and most things are heterogeneous mixture. Here it shows the beach. You have sand that doesn't dissolve in salt water. Lots of things. Crude oil, that's a heterogeneous mixture. And then we break it apart into homogeneous mixtures that are useful and maybe even sometimes pure compounds. So most everything, like I said, most everything that we care about are heterogeneous mixtures. So we are heterogeneous mixtures, right? We have skin, blood, bone. These are all different things. We're not uniform. And we also have different phases, right? I have liquid and air in me alongside solid. So, all right, other questions? And again, I'm sorry, we're changing topics yet again. All right, physical property. Physical property you can find out without changing the substance. So chemical of living creatures, it has to do with the proteins and specifically the protein shape. The proteins do all the work. So, and how do you change a protein shape? Either by pH or temperature is the most common ways. So, meaning I can move my hand, right, and works very, very well. What would happen if I had third-degree burns all over my extremity? Would I still be able to move it? No, because the heat would have changed the shape of the proteins and they no longer work. So there's lots of proteins involved in motion, right? So just the signal to go from my brain to my hand has to travel along the nerve cells. There's all sorts of things going on there, and uses a chemical called acetylcholine, actually even between the nerve cells, indicates it's in motion. And there's also chemicals that break apart the acetylcholine as well. So there's problems. Well, and then when it gets there, it indicates the muscles that, like, okay, well, it's a motion, I'm supposed to move, and then I have to tighten this way. And so then my muscles will tighten that way. Even if you go deeper, right, the mitochondria in my cells have to, through proteins, burn glucose to form adenosine triphosphate. So then it gives the kick for actually the muscles to move. And those are all carried out by protein. So if the protein loses shape, it doesn't work anymore. That's why we cook our food. If you change the protein shape, then you kill creatures like pathogens specifically. And it also makes it easier for us to break it down. So it makes it easier for us to digest our foods if it's denatured. And I'm going back to the state. Some biologists argue that if a protein denatures, that's also a phase change. So, but that's kind of above and beyond this class. But I'm also trying to give you a reason to come to class, because stuff's outside the book, if you're wondering. So, okay, then chemical property. And we care about why things change. We also care about things not changing. So what would you do? So I'm married, and I proposed to my wife with, then girlfriend, then fiance wife, with my grandmother's ring. It was a gold ring with a diamond on it. So, what if I said, like, darling, I love you. It's on YouTube, right? I love you. And my love for you is as strong as iron. And to show you my devotion, I'm going to give you this iron ring. Right? So some people are smiling. Why is that funny? Because iron rusts. The reason why we give rings of gold, platinum, silver, palladium, iridium, these kinds of metal, is because they don't react. We're giving those out of their chemical properties. So the whole idea with the ring is that it keeps a promise, and if you have the promise, it doesn't tarnish. It doesn't go away. Like, you promised me your love, and you gave me this ring, and it's 20 years now. Now it's a pile of like red brownish stuff. What does it say about your love for me? So that's why we give gold rings, because they don't rust. They're magic substances. This is what we used to think. Diamond engagement rings and gold diamond rings go back as far as the Roman Empire. They found them. They didn't cut the diamonds, but gold was magical because it doesn't rust. Like the Incans thought that gold was God's sweat. It was sun sweat. It was God's sweat. So we have a magic substance, gold, that doesn't tarnish. It's a pretty yellowish color. And we also have diamonds. Diamonds are magical because they're always cold. So you ever heard of diamonds being called ice? You get it in rap songs, why do we call diamonds ice? I mean, plastic looks like ice. Why don't I call polycarbonate glasses? Why am I like, oh, give me the ice glasses or something like that? Why do we call diamonds ice? Because diamond has a very high thermal conductivity. And if you find diamonds, they look like ice. I mean, if you see a big rock of a diamond, it looks like ice. And if you touch it, it feels cold, especially if you put it on your tongue. I haven't had that happen to me, but I've seen the big diamonds. And so it was this ancient man found diamonds, like, what is this rock? Oh, it's cold. That's weird. I'm going to put it away. Oh, it's cold. So as long as the air is not 37 Celsius body temperature, the diamond will feel cold. And so it's a magic rock. It's always cold. But the other trick is you can only touch it because they'll draw the heat from you, but then it'll reach equilibrium and it won't feel cold anymore. So, like I said, magic rock. And we would give them as gifts. We still do. Okay. And then physical change. Physical change is any change in state or appearance. State meaning solid, liquid, gas. Appearance, color. Things can change color, and a chemical change is any change in composition. So meaning atoms are exchanged. So chemical change is atoms are exchanged. So digestion. Is this a chemical change or a physical change only? So when you have a chemical change, there is almost always a physical change. I think the only example I can think of a chemical change without a physical change is the changing of the structure ordering of atoms in a crystal. So you can take iron, for instance, it can be amorphous, and then you can rearrange the atoms to a different structure, and you will still have the same iron metal, but it'll have the same properties, but it has a chemical change because then the different surfaces have different reactivities or lack thereof. So 110, I told you, is very unreactive, while the 111 surface. I know this is beyond this course, and you don't have to know that. This has to do with how the atoms are oriented in space. So the 110 surface is just, it's kind of flat, and there's just atoms all bumped next to each other. And like when iron becomes reactive, when there's holes where you can have three, it's kind of these valleys where you have three atoms deep, and then things can get in between them, and then they react along the iron surface. So then that's a case where you would have a chemical change without a physical change, but those are very rare. Almost always, when there's a chemical change, there's a corresponding physical change. So you take magnesium, and it's shiny, it's silver colored, and you burn it. It gets really bright, really hot, and then you get this white powder left over. It's not silver, it's not shiny, it's heavier, has different density, a different conductivity, and it doesn't burn anymore. So magnesium burns magnesium oxide. Magnesium oxide has a completely different list of physical properties than magnesium metal. And in fact, there was a chemical change. Okay, so digestion. Is this a chemical change or a physical change only? It's a chemical change. How about ice melting? No one wants to play. No one wants to play with me. It's a physical only. Iron rusting. That's a chemical. That's a chemical. And physical, yeah, it's both. But it's a chemical change. And iron, of course, it's silver colored like most metals are. And now it's brownish color, and it's really brittle and flaky. Okay, changing topics yet again. Okay, energy. There's a bunch of different definitions of energy. The best definition of energy is that energy is equal to the integral of the force vector dot product with the displacement. That is the absolute best definition of energy. That's a physics definition. That will cover everything. This is, of course, an intro class. So we're going to call energy the capacity to do work. Okay, that does also fit with the physics definition, but that one's much more mathematically intense. Okay, so capacity to do work. So what I mean by that, like, I don't have any kids, but I got nephews and nieces, and they got lots of energy. I see them run around all the time. So they're jumping up and down, running around, going up and down hills. Could they do work? Yes, they have a potential to do work. They could, do the dishes. They could clean their rooms. Are they going to? No. They're kids. So energy is the capacity to do work. So we also use that colloquially as well. And we have different forms: potential energy, kinetic energy, electromagnetic. radiation energy. So potential energy, again, the old physics example. I'm going to give this book some gravitational potential energy. And now I'm going to turn that potential energy, I'm not going to drop it on the floor, into kinetic energy, right? So potential energy is stored energy. Kinetic energy is the energy of motion. So there's energy involved. And even when I grabbed the book, maybe you saw me flex my back a little bit to catch the weight of that. So kinetic energy, and then radiation, things like light. So light is a form of electromagnetic radiation. And so potential energy, I mentioned, it can be gravitational, right? It's also how our water works. Water coming from the faucet. If you ever, we don't have too many water towers here. We can also do this with pressure. Like you can have a pump and you can put pressure in the pump. But we tend to put our water storage facilities up high. I guess I have seen them up in the hills. You see that we don't have them in towers. The mainland's really flat. They put water in towers. And here we just put them on top of hills. And you can see them we usually paint them like green or something like that, green or brown, the big cylinders. They put them up high because they don't require a pump. So when you open up your faucet, you're just removing a screw from a line. So it's like this kind of this cylinder going out, and you turn the faucet, you take a screw up, or a needle, I should say, and then the water flows through that hole, and it doesn't require a pump. So it's energy stored by gravity. It's just water flowing downhill. There's the faucet. So we can store energy by gravity. We can also store energy chemically. So in your food, when you say this chocolate bar has 100 calories, what does that mean? That has the energy equivalent in that food is equal to 100 calories. So if I burned that chocolate bar, I could take 100 grams of water and raise it 1 degree Celsius with that energy. So calories in food are an example of stored chemical energy. And I can take that energy from a chocolate bar, and I can go for a run. I can turn that stored chemical energy into kinetic energy. So what about temperature? What type of energy is that? Temperature is kinetic energy. So temperature is a measure of how fast things are going on a molecular level. So if you take pizza, if you have cold pizza from your fridge, you're like, I want to warm this up, so I'm putting it in the microwave. And now you don't like that, you prefer a pan, or you like the cold pizza? Okay, that's another way. Fine, we'll use a pan. Frying pan. Put the pizza in a frying pan, and the heat goes up, and now you have warm pizza or hot pizza. Is there anything different, chemically speaking, from cold pizza and hot pizza? No. Chemically, it's the same, but it's different. What's different? It's how fast the atoms and molecules are moving inside the pizza. So we'll talk about this a little bit more when we talk about temperature. But so temperature is specifically translational kinetic energy. So you have an atom in space and it moves around like this. This is known as translational kinetic energy. So I'll also illustrate. So I'm moving very translationally right now. Is there any other way I can move? No? I can rotate. Is there any way I can move? I can shake, vibrate. Rotational energy, microwaves. If you hit something with a microwave, it makes things rotate. So water molecules, so oxygen, hydrogen, hit it with a microwave, it rotates. And then, so you have two water molecules and they start rotating faster. What happens? Then they collide, so they're moving slowly, and then they collide, now they go faster. So that's how a microwave oven heats things up, is it hits the rotational energy, and then by molecular collision transfers the rotational energy into translational energy, thereby increasing the temperature of whatever you put in the microwave. So also vibrational infrared light increases the vibrational energy levels of things. So when you put your hand over a fire, like, ooh, I can feel that heat. You're making the your whatever it is, like your hand or whatever you're putting over, you're making the molecules vibrate. Then by molecular collision, then turns into temperature. Same thing. So, and with temperature, so maybe you've heard of absolute zero. Absolute zero means no translational motion. So absolute zero is when they're not moving. They're still moving, so if you have water at absolute zero, it still rotates, it still vibrates, but it doesn't move around. It just stands still. That's absolute zero. So, okay, so kinetic energy, temperatures, kinetic energy, radiation. We'll talk about that much more. I don't want to get into much now, into chapter 7. And also, I guess, chapter 5, too, talking about gases. All right, changing topics yet again. Talk about the 4 fundamental forces. And you've noticed that I've listed 5 there. So, what good is class with me unless I say something and contradict myself soon thereafter? Okay. So, the fundamental forces, this is kind of a hangover from physics. The 4 fundamental forces used to be these 4. Okay, so there's gravity is the weakest of the forces. It's ever positive. So both matter and antimatter feel gravity. So what is antimatter is the next question. Antimatter is the same thing as matter except with the charge and the handedness of spin. So what is a handedness of spin? We'll talk about spin more in chapter 7 and 8. It has to do, certain things have spins. Actually, everything has spin. It has to do with the magnetic field of it at any given point in time will point in a certain direction. So, everything we do for matter, we follow what we call the right-hand rule. If you've taken physics, if you have a wire, you put current through a wire, the current's going this way, and the magnetic field of the wire, by the right-hand rule, you will have field lines that go in this direction around the wire with a current going this way. That's the right-hand rule. If you had positrons flowing along the wire in the same direction, they would be left-handed. The magnetic field would be opposite with this handedness. So that's what I mean by antimatter. And gravity is the same for both. It's both matter and antimatter have the same magnitude of gravity. Electromagnetic field, chemistry is really just a subset of this. This deals with the idea, simplest terms, like charges repel, different charges, unlike charges attract. So positive, negative attract, negative, negative repel. And this is much bigger than that. So then nuclear weak, protons and neutrons are made of smaller particles called quarks. And what binds quarks together is the nuclear weak force. Nuclear strong, actually the nuclear weak and the electromagnetic force, turns out these are actually the same. So you can say, oh, there's only 3 fundamental forces. So when you see fundamental forces, you can see anyone say 3 to 5. Nuclear strong, so the idea with this, so protons are positively charged, and in a nucleus of an atom, you have a bunch of positive charge in a really small area, but positive charges repel. You need a stronger force to overcome the repulsion of those positive charges, and that's the nuclear strong force. So this is more or less our fundamentals of our understanding. Then we have dark energy, already mentioned, with the expansion of the universe, or seeming the expansion of the universe that we have no way of explaining other than this word dark in front of it. So, but with that, so yeah, I'm kind of saying like, so chemistry is kind of the subset of the second force there. Any questions? All right, the metric system. If we were anywhere but the United States of America, then we wouldn't have to teach this in class. But the rest of the world, England does a little bit. They still use inches and miles. They don't use pound. They tend to say stone. Like, how many stone do you weigh? Like when I was in England and Ireland, like, I don't know. How big's a stone? So everywhere else uses the metric system. So they use gallons, they use liters, they don't use pounds, they use kilograms. So the idea with the metric system is this is an engineered system. It's also nice by that everything is a factor of 10. So whenever you do a calculation change or a calculation with different units in the we call it the imperial system, everyone else calls it the American system, there's always some factor that you have to do
In calculus, it's called the Jacobian. Metric system is always factors of 10. But I mean, you look at inches, 2 miles, inches, 12 inches in a foot, and then 5,280 feet in a mile. So you have to like remember all these things in your head. Whereas metric system, it's all factors of 10. And it's also engineered. So the length is a meter. It's about this long. It used to be a distance. It was a distance, I think, from the equator to the North Pole divided by a certain value. And now we define it differently. We do it by how far light travels and by time. We actually have time and length interchangeable with our definition. The second is tied to the meter. The kilogram, this is something that's going to change. It was originally engineered to water. So a liter of water is a kilogram of water. So a meter, you have a meter, a tenth of a meter. So a cubic decimeter, a cube, that's 1/10 of a meter of water is at 4 degrees Celsius is a kilogram. So that's a kilogram. Or a cubic centimeter of water at 4 degrees Celsius is a gram. So right now, we define the kilogram as a block of platinum. So our measure of unit for a kilogram is a block of platinum. And the problem is that they don't match, and they're also getting lighter. They're evaporating. So we may change the definition of kilogram to be, they want to change it to a sphere of silicon. So that will also change the mole. The mole is based off of carbon-12. So we might change it in the future to silicon. And then temperature, Kelvin or Celsius. So Kelvin is the absolute form of Celsius. 0 Kelvin means no translational motion. Celsius is at sea level. Water freezes at 0 degrees Celsius, boils at 100 degrees Celsius. Okay, and current, ampere, you probably have heard of that before. And then no one uses luminous intensity anymore, the candela. People usually use power, use watts or joules for light intensity. I mean, watts is power, it's energy divided by time. Joules is more commonly used for light intensity now. But we still, it's one of those that we don't really use anymore. Even electrical current amperes, we usually break it down to charges of an electron or a proton for that fact. So, okay. And then we can derive some of that. These are the base units, and we can do like length. And then we can use a prefix multiplier, like I've already used before. And so, which means that I can do a base unit like a gram or a kilogram. So I'm 260 pounds, that's about 118 kilograms. So something that weighs a kilogram, liter of water. So that's about a liter of water. I mean, 100 is not so big. So something really small. An electron, it's 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron. So minus 31. And the sun is 10 to the 20 or 30th. I don't know. Where's my, why do I remember that? Okay. This is why things are useful. What is the mass of the sun? It is 2 times 10 to the 30th kilograms. So that means that I'm about, the sun is 10 to the 28 times as massive as I am. Okay, right? So, but I can use the same unit, a kilogram, and I can describe, you know, what's in that container, me, the sun, and an electron, just by using then a prefix multiplier. That's what the other power of the metric system is. And we also have certain terms. So they're missing some of these. So deca means 10. Hepta means 100. Kilo is 1,000. Then the 10th. Deci is 10th. Centa is 100th. Milli is 1,000th. Then there's micro, nano, pico, femto, and atto getting smaller. And then bigger. You're probably familiar with this with computers, though. Kila, mega, giga, tera. You probably already know that from bytes. So, and then penta and exa. So eventually we'll have petabytes and exabytes. So, although it's not proper, that's really A byte is actually 1,024 bytes. Or sorry, a kilobyte is 1,024 bytes, and a byte is actually 8 bits. So it's a different system, but use is similar to our base 10. Okay. So how are we doing so far? Questions? All right. Now let's talk about different properties. Extensive properties depend on the amount of something. So volume, mass, these are extensive properties. Intensive properties do not depend on the amount. So conductivity, density, these kind of things. So what's the density of water? Well, I mean, we just did, for those of you who had me in lab, we just had some experiments. With an experiment, we used the density of water. It's about 1 gram per cubic centimeter. Does it matter if I have a droplet of water or this much water or an ocean of water? No, the density at a temperature is not going to change. What will change is the volume, mass, that kind of thing. So that's the difference. And I mentioned density, and it's if you are less dense than what you're in, you can float in it. So I think there was a problem in the book about this. So it works by something called the buoyant force. So, here's my beautiful artwork. So if you've ever gone swimming, I know some people don't swim, but if you ever see people swimming, if you don't swim, you notice that when they're sitting there, you can see their heads. And the idea is that whatever you've displaced from the water, the weight of what you've displaced equals your weight, and you will go up to that. So if you, I notice I could swim. I float better in salt water than in fresh water. Why? Because salt water has salt in it, it's more dense. So it's slightly more dense. So you will float higher in salt water. I've never been to the Dead Sea or the Great Salt Lake. That's 25. It's brine. It's 25% salt. People tell me it's really easy to float in that. So then you float much higher. My old chemistry teacher would talk about this experience he had. He went to the Kodak plant for film back when we had film and cameras, and they had this big 55-gallon drum of mercury. They just tell people, can you stick your arm into that big vat of mercury? And like so 7 or 60 milliliters of mercury is the same as 10 meters or 33 feet of water. So if you stick your arm halfway in, that would feel like here it would feel like your hand is like 20 feet underwater. And like of course you push down and like whoo, and your hair flies out, and like it's like that felt so weird to feel like so much pressure on my fingers. So mercury you can really float on. Of course, mercury vapors are very dangerous. They don't do this anymore. So, but in the ancient Egyptian tombs, they would have liquid mercury around them, like around the. So I wonder if some of the workers there would ever just like, oh, I'm gonna lie in this mercury. There's some pictures of people doing that, like lying in mercury. There's like, oh, just floating on the top. Mercury is 13.8 times the density of water, so not a lot of mercury has to be displaced. Whereas water, we're pretty close to the density of water, so we're up to our necks, kind of thing. And the force that puts you up, I said, it's a buoyant force. We don't have them here in Hawaii, but hot air balloons. You ever seen them? You take cold air and you heat it up. It expands to a hot air balloon. The amount of air it pushes away equals the weight of the balloon plus the basket and passengers, and it'll start to float up. It'll rise until the air becomes thin enough, and then at that point in time, the weight that it's displaced is equal to the density or whatever. The weight of the air displaced equals the weight of everything. And then the hot air balloon won't rise anymore. It'll stop there. So, okay, I guess oh shoot. I guess we are done as right now. The minute's over. Okay, we are done now. Let me know if you have any questions. You can always come after me after class. I know I don't have office hours until 4:15, but if you have like a quick question, you can always come and ask me. That's pressing. Or you can also talk during lecture. That's fine too. But, all right, I'll see you next class.
Oh, nice.